Hi everyone, my name is Swapnil. Today I'm going to talk about MoEvement, a fast and reliable in-memory checkpointing system for MoE models. This is joint work with my advisor, Professor Christos Kozyrakis at Stanford. Hyperscalers today are using tens of thousands of GPUs to train massive models for weeks or even months. At this scale, failures are quite common. A recent report from Meta projects MTBF of 2 hours for training jobs with 16,000 GPUs. This number drops to just 15 minutes for training jobs with 130,000 GPUs, making efficient fault tolerance imperative to maintain productivity at hyperscale. Checkpointing continues to remain the canonical mechanism for ensuring fault tolerance. Throughout this talk, we will use the standard practice of using mixed precision training. In such a mixed precision training recipe, we periodically snapshot FP32 model weights and optimizer state, which together are termed as training state, to CPU memory and then asynchronously persist it to durable storage. On this slide, you can see 5 such checkpoints taken every 10 iterations. In the event of a failure, in this particular case, iteration 26, all workers must revert to the most recent checkpoint, in case checkpoint 20, recompute any lost iterations, in this case iterations 21 through 25, and once completed, we can resume training. In context of checkpointing, there are 2 common metrics which dictate training efficiency. First, checkpointing overhead. As the training state is updated each iteration, if a snapshot time is greater than iteration time, we are forced to stall training until the snapshot completes. This results in a steady state overhead that you pay every iteration, and to amortize this overhead, one commonly applied solution is to increase checkpoint interval. On the other hand, a second metric of interest is recovery time. This is the time it takes to bring the model to the same training state as it was prior to interruption. Expected recovery time often scales linearly with checkpoint interval. That brings me to MoE models, which have recently gained prominence as a scalable and compute efficient means of training LLMs. They replace dense feed-forward network with many parallel subnetworks known as experts. Each of these experts is selectively activated based on a learned gating module. And this selective activation enables MoE models to scale total number of parameters while maintaining sublinear growth in computational cost. Due to their higher cost efficiency, MoEs underpin several frontier models across OpenAI, Anthropic, Google, Alibaba, and DeepSeek, to name a few. While improving efficiency, MoEs also introduce new challenges for checkpointing system. Let's take an example. Here we have 2 models from the DeepSeek family. One is a dense model and has 7 billion parameter models, all of which are activated for every token, while its MoE counterpart has 16.4 billion parameters and only 2.8 billion parameters are activated for each token. Interestingly, both these models, despite having different total parameters, share the same iteration time. Because of this, the checkpoint size for the MoE model is 2.3 times larger than its dense counterpart. Consequently, its checkpoint time is also 2.3 times larger. This results in a training stall for 3.2 seconds. And to amortize this overhead down to just 1%, Gemini, not the AI model from Google, but a checkpointing system from SOSP 2023, must increase the checkpointing interval from 1 to 110, resulting in the expected recovery time to inflate by 50x. As a result, practitioners are left with a very difficult choice. You either prioritize steady state overhead by opting for a large checkpointing interval, which amortizes the cost, or prioritize fast recovery by opting for a small checkpoint interval, both of which result in low training efficiency at high MTBFs. MoEvement breaks this forced trade-off and allows practitioners to prioritize both. We do so by making 3 observations. The first one being that existing checkpointing techniques treat an MoE model as a monolithic block, And so even though in the toy example you see there are 6 operators, each of them are independent, we treat them as one holistic block and try to checkpoint either the state of all operators or no operators at all. In this toy example, you would see for 6 operators, the dense snapshot includes all 6 of them. We notice that this is unnecessarily restrictive and treat each operator as independently checkpointable. This allows us to right size a checkpoint by only selecting a subset of operators. In this example, we only snapshot up 2 operators, E1 and E2, in iteration 11. Second, our second insight builds on top of the first one. We can capture all operators by incrementally capturing a subset of them. In this example, in iteration 11, we captured E1 and E2. In iteration 12, we captured E2 and E3 and E4. And finally, in the last iteration, which is iteration 13, we captured NE and G. Across these window of 3 iterations, we have captured all 6 operators. In addition to capturing the 6 operators, movement also has to capture a few additional states to make sure that correctness is not compromised. I'm going to discuss how we use this additional state in a few slides. But the main takeaway here is that by spreading the work over a sparse checkpoint window, we ensure training is never stalled due to checkpointing. And in the paper, we discuss how this window can be dynamically picked depending on the model and the hardware characteristics for your training cluster. That brings me to how both of these look like on a timeline perspective. At the top, we have dense checkpointing, and at the bottom, we have sparse checkpointing. Our view begins from iteration 10, which has just completed. At this point, dense checkpointing initiates a dense snapshot, which takes longer than the time it takes to run iteration 11, and therefore ends up stalling it. On the other hand, sparse checkpointing is able to completely overlap with the training iteration, and therefore the iteration finishes faster without any stalls. Further, dense checkpointing has to amortize this overhead by increasing the checkpointing interval. In this example, the checkpointing interval is extended to 10 to make sure that the overhead is amortized. In sparse, because there is no overhead to amortize, we continue checkpointing the sparse snapshots at each iteration. Finally, with dense checkpointing, each dense snapshot is a checkpoint because it contains all operators. In context of the sparse checkpoint, our checkpoint spans 3 snapshots, and therefore the window W sparse, which is the window of sparse checkpointing, is set at 3. And across the same number of iterations, we are able to capture 5 checkpoints, while dense is able to capture only 2. Now, at this point in time, you might be wondering, how exactly do we recover from this sparse checkpoint? So for that, we rely on incrementally reconstructing a dense checkpoint from multiple sparse checkpoints, and we do so by selective recomputation. So when loading a sparse checkpoint, each operator is classified as either active or frozen based on the availability of its FP32 model state. Recall, our sparse checkpoint consists of a couple of things. For some operator, it consists of its FP32 model weights and optimizer. In mixed precision training, these FP32 states are used for the optimizer step. And for other operators, we track its FP16 model weights, which are being used for the computational step. So at any point in time for an operator, if you have its FP16 model weights, you can run its forward and backward pass, but you cannot run its optimizer step. And if you happen to have both FP32 model and optimizer state, only then can you run the optimizer step. So building upon that, we classify each operator at recovery time into 2 categories, active and frozen. Active operators have access to their FP32 model state, and they participate in forward, backward, and optimizer updates. The frozen ones only have their FP16 weights and can only participate in the forward and backward pass, thereby computing the activations and the gradients, but they skip the optimizer step. To concretize this, let's look at an example of how we can go from a sparse checkpoint to a dense checkpoint. In this particular case, we are working with our favorite toy example. It has 6 operators: NE, G, E1, E2, E3, and E4, and they might have FP16 and FP32 state. We load the first sparse snapshot, SS10. We have 32-bit state for E1 and E2, and for the remaining 4 operators, we only have their FP16 state. Therefore, NE, G, E3, and E4 remain frozen, and only E1 and E2 recompute their gradients, refresh their optimizer state, and update it from O10 to O11 and weights from W10 to W11. At this point, we drop the FP16 state because it is stale, retain the FP32 state that we have refreshed, and load the next snapshot. At this point, E3 and E4 receive their FP32 state from the snapshot, E1 and E2 retain their newly computed state, and NE and G only have FP16. Like before, the operators with 16-bit state are frozen, everyone else is active. The active operators compute their optimizer update and refresh their weights and operator states from O11 to O12, W11 to W12, and at this point in time, NE and G drop their FP16 states. Finally, we load our third checkpoint from the sparse checkpoint window. Now, all 6 operators have their FP32 state. They are all active, and they finally move to their 13th iteration state. This, by the way, is the same state as you would have captured if you would have taken a dense checkpoint. So, how many iterations do we have to compute as part of this sparse-to-dense checkpointing operation? It turns out in the paper we can show that we can bound the number of iterations that you must recompute to 3/2 W sparse, and the dense checkpointing techniques also have to run recomputation. In their case, their recomputation is bounded by half times D checkpoint interval, and as long as W sparse is less than 1/3 the D checkpoint interval, the amount of computation is lower. Looking at the eval, movement is built on top of deep speed, and for our training runs we use deep speed and 0, 1. It is evaluated using 96 NVIDIA A100 GPUs, each of them connected via an 80 Gbps interconnect, and we are trying to train a DeepSeek model with 16.4 billion parameter models, 64 experts, of which 2.8 billion are activated. We vary the MTBF from 2 hours to 30 minutes to 10 minutes over a 12-hour long run, and we compare our checkpointing system with CheckFrec, a paper from FAST21, and Gemini. All 3 of these systems maintain synchronous training semantics, which means that there is no impact on the model quality at the end of the recovery. First, let's look at checkpoint sizes for each of these systems. On the x-axis, you have the 3 systems. On the y-axis, you have snapshot size. Lower is better. Unlike CheckFrec and Gemini, which must checkpoint every single operator in their snapshot, movement only has to checkpoint 1/6 of the state, and therefore it is able to reduce the checkpoint size by a factor of 4. There is, as I mentioned earlier, there is some extra state that movement has to maintain to ensure synchronous training semantics, and that's the reason why we are not able to reduce the checkpoint size down to 6 times smaller, but still 4 times. Let's look at the checkpoint overhead. again, on x-axis we have the systems, on y-axis we have time, and in this particular case we have two bars, one for the snapshot time, the time it takes to capture the checkpoint from GPU memory to CPU memory, and then we have the iteration time. All three systems have the same iteration time, but because checkfrec and Gemini have a snapshot time which is higher than the iteration time, they stall the training iteration by 4 seconds and 3 seconds respectively, and must increase the checkpoint interval to amortize its overhead. On the other hand, movement is able to perfectly right size its snapshot to fit within the iteration time, and therefore does not have to amortize any overhead. Because of this amortization, checkfrec must increase its checkpoint interval to 124, Gemini to 92, while movement is able to create one checkpoint every 6 iterations, because in this particular case the sparse checkpointing window is 6. We made sure that the checkpoint interval was selected such that each of these systems has each of the system has a checkpointing overhead of 1%. This has a direct impact on mean time to recovery. For checkfrec, which has the highest checkpointing interval, also has the highest mean time to recovery, followed by Gemini, and finally movement. Movement is able to reduce its mean time to recovery by almost 20x. Finally, in terms of training efficiency, we have 3 different MTBF values, 2 hours, 30 minutes, and 10 minutes. On y-axis, we have the number of iterations. Higher is better, and we are trying to track how many iterations each of these systems were able to complete over a 12-hour run. As you can see from the plot, movement is able to improve the number of iterations completed by 8%, 17%, and 41% across the mean time to recovery windows. There are more evaluation in the paper where we study the scalability, break down the performance, study how low precision training regimes affect all of these systems, and how we can recover from concurrent failures. In a nutshell, movement incrementally snapshots subset of operators ensuring low overhead, high frequency checkpointing. By using sparse to dense conversion, we can reconstruct a dense checkpoint from sparse snapshots, maintaining synchronous training semantics. Movement reduces the recovery overhead by up to 20x and speeds up training by up to 40%. The code for movement is open source, and with that, I'm ready to take any questions. Thank you.